Hello friends, this is Vishal Nikam, working as an assistant professor in Arts, Commerce and Science College, Onde. Today we are discussing on the examples of the cosets. So first example is, because in the last lecture we have studied about the definition of coset. So in this video we are discussing examples of coset and some related theorems to coset. So first example, let capital P be the vector space of two-dimensional real number and the subspace is what? Capital W is equal to set of all the points on the line y is equal to mx. So what is the line y is equal to mx? It is a straight line with slope m and passes through origin. So this is the line y is equal to mx. This is our x-axis, this is our y-axis, and this is origin. So it has uncountable number of points. This line y is equal to mx. So this set W is what? Set of all the points on the line y is equal to mx. That is y is equal to x comma y such that x comma y belongs to R. But here the y is what? Y is equal to the points mx. So I am replacing this y by mx. So no need to consider x. So W is what? Set of all the points x comma mx. This is what our subspace of R2, and we know that this is the subspace of R2 by applying the condition of addition and scalar multiplication. Now we have to find coset of this set. In order to find the coset, we have to consider one point from the vector space P. So consider P is equal to A comma B belongs to R. P is equal to A. Because it is two-dimensional vector space, so it has ordered point A comma B. Then A comma B plus W is equal to, what is this? A comma B plus small w, where small w belongs to capital W, is equal to small a comma b plus w belongs to what? Capital W, and the members of the capital W are in this form, x comma mx. So w must be x comma mx, where this x belongs to R, and this is fixed real, which is now coordinate wise addition gives a plus x comma b plus mx, where x belongs to R. Can I write this as x dash, and this is suppose y dash, where x belongs to R. Now this is what? Collection of all the points slightly shifted or passing through a comma b. Because if we substitute here x equal to 0, ultimately this mx will be 0, and this point is what? A comma b. So it is what? Set of all the points passing through A comma. This is what? Coset of W by this element A comma B. Coset of W by this element A comma B of P. This is coset of W of V, coset of the subspace. So this is first example. Now consider the second example. Here consider the vector space P is equal to R3, that is three-dimensional vector space, and the subspace W is equal to suppose we consider any space. Suppose we consider the xy plane. Suppose we consider the xy plane. Then what is the equation of xy plane? Z must be 0. X comma y comma 0, where x and y belongs to R. Now consider the point P belongs to R3. P is equal to the three-dimensional point ABC. Then the coset of W in V by this element is P plus capital W is equal to P is what? This ABC plus capital W is nothing but small w, where this small w belongs to capital W, which is equal to ABC plus small w has the point this xy0, where x and y are real numbers, is equal to a plus x, b plus y, 0, c plus 0, x comma y belongs to R. Again, this is nothing but the plane which passes through this point ABC. This is nothing but the plane passes through this point ABC, and we can denote it as x dash y dash c, where x dash y dash belongs to R. This is nothing but the plane passing through the point A, B, C. Okay, these are the two examples of the coset in the vector space R2 and the vector space R3. Okay, so now we proceed to the next two important theorems related to the cosets. Two important theorem related to the cosets. Now we will discuss about the theorem. First one is any two cosets for a vector space V. Any two cosets of W in V are either disjoint or identical. That is, let may be any vector space, and if you consider any two cosets, then they are either disjoint or identical. What it means? That is if V1, V2 belongs to capital V, then capital is what? Vector space, and W is a subspace. Then either P1 plus W is equal to P2 plus W, or P1 plus W intersection P2 plus W is what? Is what? Empty. That is, any two cosets are either disjoint or identical. Okay. That is, if there is at least one element common to these two cosets, P1 plus W, P2 plus W, that is, if at least one element is common to these two cosets, then they are equal. जे काय तर ते दोन एकतर इक्वल असतील किंवा ते डिजॉइंट, एक की एलिमेंट कॉमन असणार आहे त्याच्यामध्ये किंवा ते दोन इक्वल असतील. सिंपल मीनिंग आहे त्याचं. व्हेरी इझी प्रूफ. what we have given capital B be a vector space, isn't it? And capital W be a subspace of B. Consider P1 comma P2 belongs to capital P. Then to prove that, what we have to prove that? To prove that P1 plus W is equal to V2 plus W, or P1 plus W intersection P2 plus W is an empty. That is, intersection must be empty. So consider there exists X belongs to P1 plus W intersection, or in another way we can say that, now we have to prove this or this. Suppose this intersection is non-empty. Suppose what? P1 plus W intersection P2 plus W is non-empty. Non-empty, it means this implies there exists at least one element. Suppose X belongs to P1 plus W intersection, or we can say that W belongs to. You can take any notation. P2 plus capital W. Okay. Now this implies that it belongs to the intersection. It means that it belongs to both the sets. So this small w belongs to P1 plus W, and small w belongs to P2 plus W. This implies that the small w is equal to P1 plus W1, and small w is equal to P2 plus W2. This implies that P1 plus W1 is equal to P2 plus W2. This implies that P1 minus P2 is equal to W2 minus W1. Now here W1 what? W1 belongs to capital W, and this W2 belongs to capital W. This implies that is W1 belongs to capital W, W2 belongs to capital W, so W2 minus W1 is also belongs to capital W. This implies that P1 minus P2 belongs to capital W. Suppose this is an equation number 1. Suppose this is an equation number 1. Now, to prove that P1 plus capital W is equal to P2 plus capital W. Consider X belongs to P1 plus capital W. This implies that, what is the representation? This is P1 plus, suppose this is W, where this W belongs to capital W. This implies that, can I write this as P2 plus P1 minus P2 plus W. This V2 and this V2 get cancelled, so it becomes a original term, which is equal to V2 plus this V1 minus V2 plus W. Now V1 minus V2 belongs to what? Capital W. By equation 1, we know that W belongs to capital W, small w belongs to capital W. So this whole term V1 minus V2 plus W belongs to capital W. This implies that X is equal to P2 plus W dash, and this W dash is equal to P1 minus P2 plus W belongs to capital W. Isn't it? That is, this implies that X belongs to P2 plus capital W. That is, initially I had taken X from this P1 plus W and it becomes a member of P2 plus W. It means that P1 plus W is a subset of P2 plus W. This implies that P1 plus W is a subset of P2 plus W. In a similar fashion, we can prove conversely, that is V2 plus W is a subset of P1 plus W. We can prove P2 plus W is subset of P1 plus W. For this, consider Y belongs to P2 plus W. And in the similar calculation, we get Y is equal to P1 plus W dash, where W dash is equal to P2 minus P1 plus W. So this Y is again a member of P1 plus capital W. Hence P2 plus capital W is subset of P1 plus capital W. Suppose this is an equation number 2, this is an equation number 3. From equation number 2 and 3, we get, what we get? P1 plus capital W is equal to V2 plus capital W. What it means? I had taken just one element common to both the sets. What is that? Firstly, initially I had taken what element? W. W is a member. From this we get this equation. Initially I get there, suppose there exists at least one element. W belongs to this intersection. And we had proved that these two sets are equal. What it means? If there exists at least one element common, it means that both the sets are equal. In this way, any two cosets of W in V are either disjoint or identical. So in the next video, in the next lecture, we had discussed about second theorem related to the cosets.